Today we're going to continue talking about solids of revolution. These are solids formed by rotating a region about an axis, and our job is going to be to set up an integral to find the volume of that solid. So remember, the point of the exercise is not about finding the volumes of these solids. That's just the vehicle that we're using to help practice our analytic geometry skills and practice our integration thinking. The calculus part is not very expensive because I said you should calculate your integrals, your definite integrals, once they're set up by grabbing the calculating machine and getting a value around 5 significant figures. Even on the ones where it would be easy to do the integration, like when we end up with a polynomial. Bypass all that. Go directly to calculating your definite integrals by hand by using your hand to grab your calculator and punch some buttons. So we have various strategies for finding volumes of solids of revolution based on how we slice. We've talked about 2 so far, and both of those have the same basic idea. Our slice is going to be made perpendicular to the axis of rotation. And we usually call those discs and washers because it matters if the slice is attached to the axis of rotation. That is, the boundary, the axis of rotation is a boundary of the region. That means the slice will always be in contact with the axis of rotation. And so we won't have a hole in our slice. So the thinking that goes with discs and washers, we're slicing perpendicular. In both of these cases, we're slicing perpendicular to the axis. In the case of discs, the boundary of the axis of rotation is a boundary of the region. In the case of washers, the axis is not a boundary of the region. I drew these sideways with what looks like a delta y, but it's the same as if we have a delta x. That's why I just called it a delta h. So if our axis is horizontal, then it just looks like this, and it's the same calculation. So here's our next strategy. I know we've only done like a few problems. Here's our next strategy that we wanted to talk about today. These first 2 are slicing perpendicular to the axis. So you can probably guess the idea behind the shells. With shells, we're going to slice parallel to the axis. Let's first write down what we're going to be using for the volume of the slice. Let's start by just being practical and saying, here's what you're supposed to do. Here's how you're going to view it. When you decide to slice parallel to the axis, the base formula that you're going to use for the volume of the slice is 2 pi times the radius times the height times the delta variable. So when you set up the problem, if you decide to slice parallel to the axis of rotation, that means you're thinking of shells, and you're going to need 2 pi times the radius times the height times delta x. Anything that we're going to call a radius has to be measured from the axis of rotation. The axis of rotation is where the radius is 0. So if I'm going to call something a radius, it has to be measured from the axis of rotation and end at the slice. In washers, we had 2 different radii, because we went from the axis of rotation to the near end of the slice and the axis of rotation to the far end of the slice. But in shells, the distance from the slice is where our delta variable is. That's the squish. That's the squish. So I only need 1 radius. I need a height. And since I've already labeled this delta x, you can see that I'm going to call this the height. So what we want to do now is justify the use of 2 pi r h delta x. If all you care about is doing problems, that's where it starts. That's where we're going to start once we internalize this slicing parallel. Means we're doing shells, means 2 pi r h delta variable. One thing to notice, I don't have a place for a 4th one. So in shells, we don't care about the axis, whether the axis is a boundary or not. Let's justify why it makes sense to say 2 pi r h delta x. Then let's grab one of our old problems and calculate it using this strategy and see if it comes out the same. If they don't agree, then one is wrong. This is a math class. We don't get to agree to disagree. If we disagree, one of us is wrong. Maybe both of us. One of us being wrong is included in both of us being wrong. So let's talk about why 2 pi r h delta x. So let's take a look at the scenario. I know I needed space over here, and yet so let's have an axis of rotation. And our slice, I'm not going to worry about what the region is. I'm not going to worry about where my axes are. I'm just going to worry about where this slice is. So I'm going to try to make it even. So this slice is going to get rotated about that axis. So shadow is going to show up. So we're going to take this little rectangle, we're going to rotate it around this axis. It's going to hit the page there, and then it's going to go behind the page and then come back up. I only got 2 dimensions to work with, so we can't see the part where it's coming out of the page. So if we take a 3/4 view, we can't see it coming out of the page like this. If we take a 3/4, it'll just look like a rectangle from the top. So if we take this 3/4 view, we're going to see so that's what's happening. That's a representation of that being rotated around that axis. And then it'll go down behind the page. That's that inner part. That's going to be that inner radius. I'm not going to draw the outer one because you could probably guess what kind of a disaster I could make out of trying to draw all of the lines for this. Despite the fact that I made my delta x very huge at like a half a square apart. The pieces that we have labeled up here are the radius. I'm going to drop it down below the skinny part. And I wanted this height here. And I wanted this thickness, the thickness of this wall to be delta x. So what we have here is a cylindrical shell, like the metal in a can. That can has a certain radius, a certain height, and the delta x would be like the thickness of the wall. So think of the delta x as the thickness of the wall. So what we're going to do, so we've got this shell, it's like the aluminum part of a can. What we're going to do is we're going to slice the can and unroll the metal. So think of this as a can, we're going to slice it and we're going to unroll it. Here's our original rectangle. When we unroll this can, these blue circles, when we that we form when we rotate it, that's going to be unrolled into a flat line. So our shell is going to unroll into a rectangular solid. Our cylindrical shell gets unrolled into a rectangular solid. cut the top and the bottom off the can, slice it at one seam, and then unroll it into a rectangular solid. The thickness of this wall is the delta X. The height is still just the height. That blue line, the blue line is connecting the red where we sliced it. When you can see I sliced it right at the red slice. I cut the can down right at the red slice, and that's why there's some red on this side. I didn't cut it very carefully. So it's like when you're cutting some paper down a line, and sometimes like you cut some of the line off. You're like halfway through the line. Yeah, that's what's showing up over here. Here's that orange part in the middle, halfway. We just unroll that into a rectangular solid. This blue line is going to be the circumference of this circle. It's going to be the circumference of this circle. And that's what, and so this is going to be 2 pi times the radius. It is a rectangular solid, so its volume is length times width times height. Length is 2 pi times the radius. The width is going to be our delta X, the thickness of our wall, and the height is just the height. Questions? Now, a professional teacher would have just brought in a can and showed you that this cylindrical shell, which has a volume, can be unrolled into a rectangular solid. But then everybody was like, "Oh, you got to stop bringing beer to class." I'm like, "Oh, it's for a demonstration." I'm like, "Well, why don't you just use a soda can?" Oh man, then I would have to drink a soda. That's disgusting. Not that I wouldn't, but not at 8 o'clock in the morning. I mean, it's not a monster. Any questions? The important thing is this. We have these 3 different strategies, which are really 2 different strategies. We've got these 2 different strategies, and you get to decide what strategy you're going to use. If you decide to slice perpendicular to the axis of rotation, then you're doing discs or washers. That depends. Now, then you just look at see if the axis of rotation is a boundary of the region or not. But slicing perpendicular, you're thinking discs or washers. Pi r squared h or pi times r squared minus r squared times h. Or you will decide to slice parallel to the axis of rotation, in which case you're doing shells, and you just start off by writing 2 pi r h delta variable. That one's going to change. To be a delta x or a delta y. The way I've drawn it here, it was a delta x, but it could just as easily be a delta y if we're slicing parallel to the axis of rotation like this. Delta x, or delta y, delta x. Any questions? This is the way it's going. This is the way these problems work. You look at the region, and the axis of rotation, you decide what slicing strategy you're going to employ, perpendicular or parallel. When you decide that, you just write down what you're going to use for your base volume. So good news, you have a choice. Bad news, you have to choose. Let's revisit an old volume. All right. So we're going to revisit our circular paraboloid. I want more. We're going to revisit our circular paraboloid that we formed by rotating this region bounded by x squared, y equals x squared, y equals 9, and the y-axis around the y-axis. Previously, we had set up a slice perpendicular to the axis of rotation. We were thinking this is a pi r squared times delta variable, pi r squared times 8. But today, we're going to do different. I put in my axes. So now we're going to slice parallel to the axis of rotation. So I pick a generic slice. So here's my axis. So I'm going to slice this way. And I'm just going to put the slice here to give myself space to write. Once I've drawn this slice, and I know that I'm slicing parallel, so shells. And that means that my delta variable is going to be delta x, because I'm going to want to make the walls as thin as possible. So this is what's getting rotated. So it looks like I'm using a delta x. We have decided to slice parallel. So we immediately write volume of the slice is 2 pi times the radius times the height times the delta variable, which is delta x in this case. I chose my strategy, slice parallel. I wrote down my volume, 2 pi times the radius times the height times delta variable. I looked at my image, I saw that the axis was vertical. The equation for the axis of rotation is x equals 0, so I'm going to be using a delta x. Now I need to take my radius and my height and figure out where they are in my picture over here. The radius is always measured from the axis of rotation. So there's the radius. And then the height is going to be the only thing that's left. Here's the height. always going to be perpendicular to the radius. Now I just need to write the radius and the height in terms of x and y. So that means I need to know where x and y are. I'm going to pick up a point where the slice intersects this y equals x squared. So I can label x and y. This is all just labeling stuff. These are all the things that happen because of the choice that we made to slice parallel. Once we said slice parallel, we just automatically 2 pi r h delta variable. Go to your picture, label where r and h are. Then, since you're going to have to write r and h in terms of the delta variable, label where x and y are. Then we can start seeing what's what. Here's an easy one to grab. The radius is in the same place as the x. So it looks like r is equal to x. And since we're doing a delta x, that works for me. I need to write r and h in terms of the delta variable x. If r is equal to x, we're all set. This h is going to be a y until we turn it into an x. So the h is going to be at the top 9 and at the bottom the parabola. So 9 minus y . If the whole thing is 9 and one piece is y, then the other piece is 9 minus y. The whole is 9, one piece is y, the other piece is 9 minus y. Nine minus y is not going to work for us because I need delta x. Fortunately, y is equal to x squared. So I can write my height as 9 minus x squared. So the volume of my slice is 2 pi times the radius, x times the height, 9 minus x squared times the delta variable, delta x. Then we add up all such slices into a Riemann sum with the number of slices goes to infinity, and that will produce our definite integral. So our total volume, I'm going to factor out the 2 pi. We have the integral of x times 9 minus x squared. Our delta x gets written as our continuous dx. Then the last thing we need to do is figure out what values of x tell us about slices. The slices start at 0. And the slices are all done at 3. So here we have an integral of a polynomial, which would be easy to do by hand. So I'm going to use my hand to grab my calculator and do 2 pi times math 9. I'm not even going to multiply this out. That's exactly how lazy I am. So x times 9 minus x squared with respect to x from 0 to 3, it's x. And we get 127.23, which is the same thing that we had before. 81 pi over 2. Any questions? Everybody okay? Yes. Oh, I just took my 127.23 and divided it by pi, and then that tells me what's left over. Then I cross my fingers that this still remembers the 40.5. Or that it wouldn't display with like 40.4 and then a bunch of nines. If we were still at the stage where I was concerned that that I wanted to find out if you could still integrate polynomials, I would have just said, give me the exact value for the volume, kind of implying that you should do this part by hand. But you'll notice that if we just divide out the difficult part, the irrational parts, you can say the exact value is 81 pi over 2. At this point, I trust that if I actually integrate x times 9 minus x squared from 0 to 3, you'd be able to do that. So let's cut that part out and just focus on what the problem is about. The 127.23 is only useful so that to compare it to calculating volume in other ways. So it's useful to us for that reason. It's useful for me because I'm trying to grade your work. So if you're like all 127.23, I'm pretty sure that the integral that I'm about to look at is going to have the correct endpoints and the correct formatting. And I'm pretty sure that you're going to be using the correct volume of the slice. And I'm pretty sure that your diagram is going to be labeled correctly. So there's diagram, development, definite integral. There's no D word for answer. Solution, no, there's no, it really kind of pisses me off for years because there's like diagram, development, definite integral, no D word for this. Done, the answer, I don't know. Nothing works. At this point, I think someone could come up with something that fits perfectly, and I wouldn't be happy about it because I've been so unhappy for so long. That's just been normalized. So, because someone suggested done, and if they had done that the first day that this started bothering me, I'd have been like, "Oh, perfect. Diagram, development, definite integral, done." And it'd be kind of, but now I'm just like, I'm just so pissed off about this whole thing. It's all over. But those are the 4 things that I'm going to look at, but not in that order. Things I care, so what happens is I look at your answer. See, that's the problem. I can't say, I look at your done. See, it doesn't make any sense. So I look at your answer. If I see that it's incorrect, I go look for where you made a mistake. I look for the most popular places. I look back at the definite integral, and I'm going to look to make sure that everything's written in terms of the delta variable. Actually, that's a development thing. When I look at the definite integral, the first thing I look at is the interval. It's a dx integral. Did you integrate over all the values of x? That's the first mistake. That's the mistake we're going to make in the definite integral slice. If the equation that we're trying to integrate is incorrect, that happened in the previous step in the development. The definite integral, this big decision that we made there, is integrating from 0 to 3. So when I look at the definite integral, I look at the interval over which you are integrating. If I see from 0 to 9, that shows me where you don't understand the problem. We're integrating dx. The y's go from 0 to 9, but the x's go from 0 to 3. So if those are all correct, I look at the development phase. I say, okay, everything's in terms of x, and there's a delta x. And I can see a 2 pi radius height delta x. And then I look at the diagram to see where things are labeled or aren't labeled. So if there's something wrong back here, I backtrack to find out where that is. The two most common in the definite integral, you're integrating over the wrong interval. That's the most common thing. 0 to 9 instead of 0 to 3. Or for the delta y one, 0 to 3 instead of 0 to 9. The other most common place to have a mistake is over here. You don't want to label your diagram. It's too much work. So I'll see a diagram with the parabola and the slice drawn in it, but then the slice does not match the volume of the slice that you're using over here. And you didn't allow yourself a chance to be reminded of that because you didn't take the stuff that you found in the volume of the slice, R and H, and go label them in your diagram. Diagram, development, definite integral, answer. I look at those things in reverse. For you, they show up in that one. How's everybody okay? So here's another thing. Once I start asking you to find the volume of the solid revolution, it is not one problem anymore. It's two problems. Slice perpendicular, slice parallel. Make sure that they match. Then once we start, I'm going to cut out the middle term here. Once we start realizing that we prefer one over the other, we just tend to always do that. You're like, oh, slicing parallel is the way. I don't want to have to worry about whether there's a hole in the middle of my solid or not. So I'm just going to slice parallel all the time. At which point I'll say, I see you're slicing parallel all the time. Let me give you a region for which that is very inconvenient. All I really have to do at that point to make it inconvenient is use a function that's not invertible. So instead of using a quarter of this parabola, using both sides of the parabola. So y is equal to x squared is no problem, but x equals plus or minus the square root of y. But now that I've said that, neither one poses an insurmountable problem. Any questions? All right. In the tradition of me spending an inordinate amount of time on a small subject like trigonometric substitution or integrating rational functions, tomorrow we'll find some more volumes of regions. Maybe I'll even change up and do a different region. That's going to do it for today. I'll see you all on tomorrow. Everybody have a good day and thanks for playing.